Right. So in the last classes, we have seen about the circuit theory, right? DC circuit theory and how to handle circuits with AC sources, right? So I'll try to upload the tutorials. I prefer to do the tutorial once you come back to the university, but at this condition, I don't think we can have enough time after you come back to university to do the tutorials, right? So I'll try to finish it through online as well. Since you are final year students, I don't think you will have enough time to do the tutorials. Okay, so yeah, once we completed this chapter, we'll do the tutorial for all three together, and then we'll move for the last one, last chapter, which is transistors and FETs. Okay, right. So in this chapter, we are going to see about electronic materials, PN junction, and their applications. Right. So as you all know, based on conductivity, right? Based on conductivity, we can divide the materials, right? Into three, right? One is conductor. Can you see the letters? Is it clear to you? Or they are smaller? Hello? Those who are using mobile phones. Can you see the letters? I'm asking you, students, please reply in chat. Okay, so yeah, those who are using mobile phones, if you cannot see the letters or if they are small, please let me know, right? Just send me a message in chat. I'll try to write it a bit bigger, right? So conductor, insulator, and then we have a material called semiconductor. Right? Conductor is a material which can conduct electricity. Right? An insulator is the material which cannot conduct electricity. Conductor means all the metals, right? Like gold, silver, copper, platinum, things, right? Iron or whatever. Right? Insulator comes again paper, plastic, wooden planks and things, right? So they cannot conduct electricity. Right? Semiconductors are the materials which are partially conducting, right? Partially conducting materials. Right? They are not good conductors. At the same time, they are not good isolators. Right? As you all know, the conductivity depends on the charge carriers within the material, right? Free charge carriers within the material. If a material wants to be a conductor, that material must have enough charge carriers in its valence band, right? In an atom, right? So I'm just writing the basic OL science, right? In an atom, we have valence band, and then we have conduction bands, right? Valence band is the outermost orbit of the atom, and conduction band is where the charge, right? If you have an electron in conduction band, that can move from one atom to another, right? If you have an atom in valence band, that cannot move from atom to atom. But if you have an electron at conduction band, that can move from one to another, which creates electricity or flow of current. Clear? Right. So based on the band theory, right, we can write down the, for example, for an insulator, we have very large band gap. Band gap is if we have valence band and conduction band here. The gap between valence band and conduction band is called as band gap. Right? This will be very high. Right? This will be very high for insulators. Right? These valence band and conduction band will be overlapping. Right? For example, if you have an atom, something like this, right? This is a nucleus. This is your valence band. Sorry, yeah, valence band. Right? So whole this will be your valence band, and your conduction band will be overlapping. Right? So this will be your valence band level. This will be your conduction band level. So always you will have some free electrons. You will have a few free electrons in this conduction band, so that the material can be called as a conductor. Right? It will be a conductor. Right? It will conduct electricity. Meantime, in semiconductors, we have a positive band gap, right? But that will be smaller than insulators, right? It will be smaller than insulators. This is valence band, this is conduction band, but the band gap will be smaller, right? So that what will happen is, right? So when you are increasing the temperature, virtually you are giving the energy to the electrons at the valence band, right? For example, the energy due to temperature is, right, the voltage equivalent of temperature will be Kb into T, right? Kb will be Boltzmann constant and T is the absolute temperature. Don't worry about this equation. What you need to know is, whenever you are increasing the temperature, the energy of the electron is also increasing, right? So E, right? Energy of the electron is also increasing, right? What is the room temperature at absolute temperature? Right, will be 300 Kelvin, right? Absolute, nearly about 300 Kelvin, right? So at room temperature, or even I say at 27 degrees C, right? The energy will be Kb into 300. Am I right? Kb into 300. So it will absorb that energy, and this electron will go to the conduction band. At the same time, a vacancy will be created at valence band. Clear? So this is called as electron, and the vacancy of electron at valence band is called as a hole. Right? A hole. Right? So these two, electron and hole, will effectively contribute in conduction of electricity. Right? The electron hole will be contributing in conduction of electricity. Right. Now we'll see about the most conventional intrinsic semiconductor. Right? We have two types of semiconductors. I will explain it later. First, we'll see about, right? So what are the examples for semiconductors? Are the fourth group elements, right? Silicon, germanium, and some other non-conventional materials like titanium dioxide, zinc oxide, SNO2, right? Tin oxide. So these oxide materials are also semiconducting materials. And we have some polymer materials called P3HT, right? Polyhexyl thiopane, right? It's a polymer, like a polythene. We can make it as a thin sheet, but it's a polymer material. It's a semiconducting property, right? And also we have a E dot PSS, right? We have a few semiconducting polymer materials which are also showing semiconducting properties. Right. Now we'll see about the conventional example of silicon. Right. Silicon is a fourth group element. As you know, silicon have right. So silicon have 4 electrons on its outer orbit. right? And then all 4 electrons will be shared among the other atoms, something like this. Right? Yeah. Right? So the electrons, each of the electrons will be shared among the adjacent silicon atoms, something like this, right? But the structure is not a two-dimensional structure, right? I'll show you the crystal structure of a silicon tomorrow. We have one in the lab, but the first year lab is not opened yet. I will take that crystal structure, right? It's a 3D structure, right? This the crystal structure is a 3-dimensional structure, not a 2-dimensional structure like this on the paper, right? It will be in a 3D structure, right? Now, in this silicon, when you are increasing the temperature, the electrons at the bond will be pulled off. Increasing the temperature means you are giving energy. Am I right? So these electrons will be pulled off from the bond. Am I right? So there will be a free electron, and then there will be a hole, a vacancy of electron. Right? So these electron hole pair is called as thermally generated charge carriers, right? Thermally generated charge carriers. Why? Because this is created when you are increasing the temperature. So there will be a hole and then a free electron, right? So this free electron can move around the silicon structure, right? Silicon crystal. Similarly, right, just imagine we have a hole, right? We have a vacancy. So this electron can go and fill this vacancy, and the vacancy can be here, right? Virtually, right? Again, this silicon can move here, right? And then the vacancy will be here, right? So you can see that there is a net movement of electron in this direction, but the hole moved from there to here and here to here. Am I right? Clear, right? Whenever the electron is filling the holes, you can see that the electron is going in this direction, but virtually the hole is moving in the opposite direction, right? In the opposite direction. What is the direction of current in a conductor, right? If we have electrons moving in this direction, then the current direction will be in the opposite direction, right? See here, if the electrons are moving in this direction, the holes are moving in the opposite direction, right? So if we have a current direction in this way, right? So the electrons will be moving here, and then the holes will be moving along the direction of current, right? Look at here. When you have I in this direction, the net flow of electron will be in the opposite direction, and the net flow of holes will be along the direction of current. Clear, right? Now, see here, these electron hole pairs are created due to the increase of temperature, right? Due to Kb into T. Am I right? Due to the Kb T. What will happen if we make the temperature 0? Right? If we make the temperature 0, of course, we have 0 energy to the material, right? Means it is not 0 degree Celsius. It is 0 degree Kelvin, right? 0 Kelvin, not degree Kelvin, 0 Kelvin, which is minus 273.16 degree, right? Minus 273.16 degree, which is called as absolute zero temperature, right? At absolute zero temperature, you cannot have any thermally generated electron hole pairs. Am I right? You cannot have any thermally generated electron hole pairs. So I could say that at absolute temperatures, right, 0 Kelvin, right, the charge density, or there are no free charges. No free charges, right? At 0 Kelvin, there are no free charges. Hence, the silicon will behave like an insulator. Clear? The silicon will behave like an insulator at 0 Kelvin. But when you are increasing the temperature, you will have thermally generated charge carrier, which are very few in numbers, and those will contribute in current or contribute in conduction of electricity across the silicon material, right? Silicon crystal. Right. So what is the problem here? Since so we have pure silicon and that is insulated at 0 Kelvin, hence we call it as intrinsic. Semiconductor. Right, we call it as intrinsic semiconductor, right, which is the purest form of silicon or purest form of germanium crystal or whatever, right, without any impurities. Now we see in that there is a problem here, right? There is a problem of having this one here. What we can do is, even at room temperature, intrinsic semiconductor heavily depends on thermally generated charge carriers. Clear, right? To increase the conductivity of these materials, what we can do is we can dope other materials with the silicon structure, right? For example, silicon is a 4th group element, so we can dope with 5th group element or 3rd group element, right? Give me a second. Sorry, right? So now what we can do is assume that instead of this silicon in the middle, right, in the middle, what we can do is we can substitute this with a 3rd group element, right? For example, we have aluminium in the 3rd group. What else? Aluminium, right? Boron, aluminium. Yeah, and then at the 5th group, we have phosphorus, right? Yeah, okay, consider boron and phosphorus, right? Boron. Right, then phosphorus, right? Phosphorus will be in the 5th group and boron will be in the 3rd group. For example, If we add boron here, we know that boron have only, right, boron have only 3 electrons on its outer orbit. Am I right? So 1, 2, 3. Right? Boron have only 3 electrons on its outer orbit. Hence, of course, these 3 electrons will comes into bond, right? So there is right. And then you will have no electrons to be made it into a bond, and then that will be a vacancy, right? There will be a vacancy. I could say that the ratio between boron and silicon will be 1:1,000,000. 1:1,000,000, right? For 1,000,000 silicon atom, I will add only 1 boron atom, right? That is called doping, right? If you have high amount of boron, then that will be a kind of mixing, right? Composite. But here I am going to dope, means I'm going to add a very little amount of boron, right? Hence, there will be a free electron, right? There will be a hole or a vacancy of electron, right? So that can induce electrical conductivity, right? So that can these electrons can go there, and then that hole can virtually move along the structure. Also, at room temperature, again, you will have thermally generated charge carriers as well, right? You will have thermally generated charge carriers as well. Not only the charge carriers generated by the impurities, but also you will have thermally generated charge carriers at room temperature. So in a mixed or in a doped semiconducting material, you will have both thermally generated charge carriers and charge carriers created by doping, right? So these electrons can move from here to here. So virtually there will be, right, but effectively the number of holes will be higher. Am I right? The number of holes, right, will be greater than, right, E minus, right? Number of holes will be greater than number of electrons in this material. It doesn't mean that the material have positive charge. No, but number of holes is higher. But since the boron have only 3 neutrons, right, plus 3 neutrons and 3 electrons, the material will be net charge. The net charge of the material will be 0, right? But number of holes will be greater than number of electrons. Hence, we call it as a positive type semiconductors or P type semiconductors, right? Small p, not a capital P, right? P type semiconductors. And then what we are doing is we are doping here. We are adding external impurities to the material. Hence, it is also called as extrinsic semiconductors. Right? So intrinsic semiconductor is pure silicon. Extrinsic is the material we are adding. So we are adding external materials. Right. Now, let's see what will happen if I add a fifth group element. What is phosphorus, right? I'm adding phosphorus, which has 1, 2, 3, 4, and then it is going to have a 5th electron on its orbit. Am I right? So these will be contributed in the bonds, right? The 5th electron will be left alone, right? The 5th electron will be left alone in the crystal structure, and that will be freely moving. Similar to the p-type semiconductors, we will have thermally generated electron hole pairs, right? So in overall, in this type of semiconductor, see here, the number of electrons will be higher than number of holes, right? I could say H plus is less than E minus, right? Hence, we call it as negative type, right? Small n again, n-type semiconductors. N-type semiconductors, right? Again, it doesn't mean that the material have a net negative charge, because phosphorus have +5 charge, so 5 electrons, it will be 0, but effectively there will be higher number of electrons than holes at room temperature. Hence, we call it as negative type or N-type semiconductors, right? So we can come to a summary. I would say materials, right? Conductors, semiconductors, insulators, right? Semiconductors I can divide into two. One is intrinsic, the other one is extrinsic. Extrinsic again N-type and P-type. Clear, right? So this is what we have seen so far. So we have seen the how the electron hole pairs are generated in intrinsic semiconductors, and how we can create it, or how we can create extrinsic semiconductors of both N and P type. Okay, right now, yeah, we can move to a PN junction, right? A PN junction. Do you have class at 9 o'clock? Right, we'll see about a PN junction, right? Remember, PN, they are not capital letters. Always prefer to use small letters, right? PN junction. Right, now, for example, what I'm going to do is, we are going to have a silicon, right? So I can show you a silicon wafer. Give me a second. Yeah, so this is a silicon wafer, right? This is a piece of silicon, right? They made it into a semiconductor, exactly semiconducting silicon wafers, right? And then I cut them into pieces, right? I asked the supplier to make it into pieces, right? This I bought for my research purpose, right? So here we have two sides, right? So what I can do is this, right? Sorry, you can see that this is a small piece of silicon, right? So that is damaged, right? We need to wash it before doing any research. See here, it has a thickness, right? You can see that it has a thickness of about a millimeter, right? Sorry. Yes, the thickness of about 1 millimeter, right? So you can see it clearly. Right now, what I am going to do is I am going to make P-type semiconductor and N-type semiconductor on the same crystal, right? So this piece consists a single piece of silicon, right? Single crystal of silicon, right? So a PN junction is have a p-type doping and n-type doping in the same crystal, right? It doesn't mean that you are making p-type and n-type separately and you are bringing it together, right? For example, making a p-n junction is already you can have a p-type semiconductor, right? P-type silicon. You can purchase p-type silicon. Of course, this is a p-type silicon, right? If yes, it's down. And this is a p-type silicon, right? What I can do is I can put some phosphorus on top of it, right? Hydrophosphoric acid. Then I can heat it in an oven, right? So effectively, the phosphorus atoms will diffuse into it, right? Will diffuse into it. Already I have p-type, and then I am adding phosphorus atom to it. So effectively, half of the crystal, right? If we see from here, half of this will be right. This half will be p-type, and this half will be n-type, right? So that is called as p-n junction. Right now, let's see how the electron charge is, or electrons and hole distributed along the p-n junction. Right? Don't think that a p-n junction is made by making contact of a p-type and n-type silicon. Right? It is not possible. Right? You need to make a p-n junction in a single silicon crystal by using diffusion or any other techniques. Right. Now, consider a piece of semiconductor, right? Piece of semiconductor. As you said, this is already an n-type semiconductor. So I have a more number of electrons, right? I would make it something like this. And then what I am doing is I am diffusing p-type to the next side, or that becomes positive charges, right? That becomes excess of holes. Clear, right? There will be excess of holes, right? At this interface, look at here, these are electrons and these are vacancies, right? What they will do is simply these electrons will jump and they will start at neutralizing them, right? So these two will be neutralized. Similarly, this will be jumping and then these two will be neutralized, right? Something like this. So look at here, there will be a thin region of, right? So in this region, I could say effectively there are no charge carriers. Am I right? So both free electrons will recombine with the free holes, right? I would say holes. And then as a result, there will be no charges in this region. So I could say the charge carriers are depleted from this region. Hence, we can name this region as depletion region. Right? Depletion region. Right? But now look at here. If this electron want to go across, right? If this electron wants to join with this hole, it has to jump across these charge-free region. Am I right? It has to jump across this charge-free region. Hence, it needs a small amount of energy, right? To jump across a charge-free region, this electron needs a small amount of energy, right? And at equilibrium conditions, right? Equilibrium condition means the depletion region is fixed. At depletion region, equilibrium conditions, the voltage it requires to reach the other side of the depletion region is called as barrier potential, or we can denote that by VD, right? VD. So depletion region, hence we call, right? We can have ohmic contacts here and here, right? We can have ohmic contacts, right? So this is, since it is negative carrier side, we can call it as cathode, right? Positive side, we can call it as anode, right? And this PN junction can be called as a diode or a PN junction diode. The symbol of a PN junction diode is something like this, where this is your anode and this is your cathode, right? This arrow marks indicates the negative to positive direction, right? This is cathode, anode. So this way you will have your arrow mark here. Okay, PN junction. Right. Now let's see how this PN junction behaves whenever you are applying an external bias. Right? For example, yeah, I'll draw it again. Right, so I have a depletion region here, right? Minus here, right? So these are holes and these are minuses. And what I am doing is, right, of course, I can have ohmic contacts right here and here, right? And then you can connect it to an external battery or an external electric field. Right? This you have studied already in your A levels and O levels, right? Right, something like this. Now what I am going to do is I am going to connect the positive side of the battery to the negative side of the diode and negative side of the battery to the positive side, right? That is P side of the diode. So what will happen? Right, so the electrons will be injected from here, right? So E minus or minus charges will be injected from here, right? Those injected electrons will be recombining with these holes. Am I right? Similarly, this positive charge will deliver holes, or effectively will be drawing all the electrons, draining all the electrons from the inside, right? So effectively the depletion region, right, whenever you are increasing the voltage, the depletion region will be growing, right? It will be growing, but there will not be any current flow. There will be a very small leakage current, which is called as I naught, right? Very small leakage current, right? In terms of microamps, or sometimes it will be in terms of nanoamps, 10 to the power minus 9 or 10 to the power minus 6 amperes, right? So if you are increasing the voltage, the depletion region will get growing and growing. At one stage, the whole crystal will be depleted from charges, right? At a very high voltages, the whole crystal will be depleted from charges, right? At that time, there are no charges in the semiconductor material, right? It is kind of an amalgamated condition, right? Now, just imagine there are two parallel plates, and then you have atoms here and there. Now further you are increasing the voltage, which means you are applying an electric field, right? Plus to minus, you are applying an electric field E, which is equal to V by D. Am I right? D is the thickness of the device, right? For example, if D is 100 micrometers, even if you apply 20 voltages, 20 by 100 micrometers, right? 20 by 100 into 10 to the power minus 6, 100 micrometers, right? So 10 to the power minus 4 will be 10 to the power minus 4. The electric field will be 200,000 volts per meter, right? Will be massive, right? It will be a massive electric field. What that electric field will do is, right, if you have a silicon atom with 4 electrons, this massive electric field will pull off the electrons, right, from the bonds, right? It will pull off, and then that electron will be accelerated, right? What is the acceleration? EQ, right? The force on an electron, right? If you have a charge Q, then the force acts on the electron will be EQ, right? And then the electrons will be accelerated, and that electron will hit another electron and creates 2, and those 2 will be accelerated, and then they will hit another 2 electrons and creates 4. Like this, the carrier multiplication will happen. Clear, right? Just assume 1 electron will be pulled off from bond, that will hit another, there will be 2, and those 2 will hit another 2, will be 4, and those 4 will hit another 4, will be 8. Like this, carriers will be multiplied, and then there is a sudden increment of charge, right? There will be a sudden increment of charge, and a huge current will start flowing through the material. But once that happened, this semiconductor is gone. You cannot reuse it again, right? This semiconductor is gone. So I could say, if I apply negative to positive, positive to negative, which means at this stage, I will have a small leakage current, as I said earlier, right? This will be I naught, right? I naught. This will be a I naught, but that is in terms of micro ohms or nano ohms. But at a certain voltage, there will be a sudden carrier multiplication, and current will be massively increasing, right? Rapidly increasing. This is called as breakdown, right? Your diode is breakdown, right? Your diode is gone. It is not reversible. Once this happens, then you cannot use the diode again. You have to just reuse or use another diode, right? You can throw them and you have to replace it with another one. Right. Now let's see what will happen if we connect it in a forward bias, right? So hence it is called as reverse bias, right? Right, this is the reverse bias IV characteristic of a PN junction diode. Now we are going to see the opposite, right, which is positive, right? So of course now I have a depletion region, right? So minus plus, right? We contact. What I am going to do is I am going to connect P to P and N to N, right? This is minus to minus, plus to plus, right? So effectively what I am doing is I am injecting more electrons here and injecting more holes here, right? So effectively the number of electrons will be increasing here. Similarly, number of holes will be increasing here. Am I right? So they will start pushing the depletion region, right? They will start pushing the boundaries of the depletion region, and hence the depletion region will get narrower and narrower. Right? It will be when you are increasing the voltage, the depletion region will get narrower and narrower. At one stage, when the depletion region is small enough that the electrons can jump from this side to other, there will be a huge current. Right? So if you draw the IV characteristic, until this point, the depletion region will get narrower, and then suddenly current is started flowing. Right? There will be a sudden increment, something like this. Right? So this is positive I am doing since I am connecting plus to plus and minus to minus. Right? So if I draw, so this is called as forward bias. Right? If I draw the IV characteristics of a diode, right? Of a diode, something like this. This is I, sorry, this is V, this is I, right? So this is plus and this is minus, right? So I could say in positive, I will have something like this. And this will be my barrier potential, right? I would make it as VT, right? Barrier potential. And then at reverse bias, I will have a small current, right? Which is leakage, right? Reverse saturation current, or I naught, right? This is I naught. And then suddenly it will be breakdown, and that is not reversible. This is called as breakdown potential. Right? The breakdown potential will be much higher than VD. Right? For example, and also VD depends on the material you are using. Right? For example, for silicon, VD is 0.67 voltages or 0.7 voltage. Right? For germanium, it is around 0.3. Right? It is not exactly 0.3, but for our calculations, we are assuming it as, for silicon, it is 0.7 voltage. For germanium, it is 0.3 voltage. And this is the IV characteristic of a PN junction diode. So diode have a barrier potential D and a breakdown potential D. Right now, we'll see a hypothetical device, which is an ideal diode. An ideal device means there are no such kind of device, but we are assuming, right? They are hypothetical devices, right? We are assuming that those devices are exist, because when we are handling very high voltages, right? For example, when you are handling with 100 voltage or 200 voltage, these can be neglected, right? At that conditions, we can use the term ideal diode, right? The current voltage characteristic of an ideal diode will be something like this. Right? There are no reverse saturation currents, right? I naught of a diode, ideal diode will be 0, and then the barrier potential of the ideal diode is also 0 voltage, right? And it will not break down, right? Ideally, the ideal diode have no breakdown voltage, right? So it is clear that, right? So just leave about this breakdown point. Right, by seeing this IV characteristic, you can say that below VD, your diode will not conduct electricity, and above VD, your diode started conduct electricity. Am I right? So as a result, I would say, okay, I can draw the circuit symbol of a diode, right? If I right, plus minus, of course you will have a current through this one, and there will be a barrier potential loss. But if I interchange the diode, or if I interchange the battery, something like this, then there will not be any current through the circuit, right? I will be 0 effectively, right? So we can neglect the I naught or the small current conducting through this one, right? So this will be VD, and then this will be again VD. So we can simply say that if I connect a diode in a circuit, it will conduct electricity only from minus to plus direction, right? If the potential difference is applied in the other way around, there will not be any current flowing through the circuit. Clear? So I think that's enough for today, right? That's all about the basics of PN junction diodes. And in our next class, we can see the application of PN junction diode, right? Maybe we need another 2 class to complete that one, and we'll move it into the next chapter. Okay, so this will be the yeah. So see you on Friday, right? Friday at 7 o'clock. Okay. Right. So thank you. Any questions or doubts?